First things first, could you just introduce yourself and talk about what area of physics you specialize in and which interpretation of quantum mechanics you favor and why?
Okay, I'm Shaun Cole. I'm a professor in the Institute for Computational Cosmology here. And I work on cosmology, galaxy formation, and analysing large surveys of the universe. It may disappoint you. I don't have strong views on the interpretation of quantum mechanics. The Copenhagen interpretation is fine as far as it doesn't predict anything that is inconsistent with observations, but I don't think it can be right, and I think I prefer the developments of decoherence that it happens naturally, essentially, the collapse of the wave function, and is not something that's due to artificial measurements.
So that brings me to the next question. With regards to the measurement problem in quantum mechanics, how do you think probabilities are converted into well-defined outcomes?
I mean, the mechanics of quantum mechanics is well defined. That you have the wave function, and that determines the probabilities of different outcomes. And I say the Copenhagen interpretation tells you make a measurement and you'll get one of those values. The issue comes is what do you mean by a measurement? And that's how the whole Schrodinger's cat paradox comes about, because does the cat make a measurement? If not, and you only make the measurement when you look at the cat, then you have this strange description of the cat being in a superposed state where it's both dead and alive. But as far as anything that's you actually measure, whether it's in that state, it being in that weird state doesn't affect anything you can measure. You can't prove that it isn't. So in that sense, that the Copenhagen interpretation is fine. But so in my field, I work in cosmology, and the density fluctuations in the universe from which all structure formed, galaxies and stars, are supposed to be quantum fluctuations. So, if it really takes a human to make a measurement, does that mean the universe evolved for billions of years and our galaxy didn't form here until someone observed it? And by making observations of galaxies that no one looked at before, we're making those suddenly spring into existence? That doesn't seem right to me. And I don't think we're special. So I feel the wave function has to collapse on its own somehow.
So how much does your favored interpretation shape the way you approach quantum mechanics?
Well, see, that's where I think I don't have a strong view, because my favourite view is that there's this decoherence, and that when systems aren't completely isolated, so the ideal description of unitary evolution of the wave function is never true because they interact with their surroundings, and I think that is probably what causes what we call collapse of the wave function. But in terms of calculations I would just do it in the standard method. So it doesn't affect how I do quantum mechanics in that sense.
So according to von Neumann and Wigner, the causative agent in wave function collapse outlined by the Copenhagen interpretation is consciousness. Is this a fallacy, or do you think there is some merit behind it?
Well, that's where I think it is a fallacy. That's why I say I don't think it requires our conscious observing of a distant galaxy to make that galaxy suddenly appear. It just seems ridiculous. And what is consciousness as well? I mean, is that where did, obviously it's not just humans that are conscious, but how far down you go in small insects and life or whatever. When do they affect things? Who knows?
So before we observe distant galaxies, can you describe them in terms of superpositions like Schrödinger's cat?
You can describe the density fluctuations as quantum fluctuations, which are a superposition. And yes, until you observe those, the fluctuations in the microwave background or whatever, until the measurement's made, you could say that they're in a superposition. But I think that's what the Copenhagen interpretation would say.
So how does the collapse happen naturally if it's not to do with us measuring it?
So the decoherence picture is that this unitary evolution of the wave function, that it's not collapsing, isn't what happens when you consider how it interacts with its surroundings. And people model the evolution of a wave function coupled to a sort of thermal bath of quantum oscillators, and show that the behavior gets more and more close to the classical behavior. But it still doesn't solve the problem. It just says, you would just say all these particles are getting in entangled states, and so there isn't a solution that you can't mathematically prove that decoherence gets rid of the paradoxes you have in quantum mechanics. But I think it just has to happen naturally, because I don't believe there's a special place for consciousness in the physics of the universe.
So is non-locality an issue for the Copenhagen interpretation, and does it not violate special relativity?
So no, so non-locality has to happen in quantum mechanics and in the Copenhagen interpretation, but I think it's been proven to happen. They've produced entangled states and propagated them over large distances now, and so on. So I think it's experimentally proven, and it doesn't violate relativity, because you can't actually transmit information. So you can't influence something that's more than the causal distance away, even though you get this strange entangled states.
If we knew how to communicate sort of quantum information, would that mean that, in the sense that something is happening at a distance over which it would take longer than the speed of light to propagate, so something instantaneously is happening over a non-local system, if we understood how to communicate quantum information, would that mean that would that have any implication for relativity?
So I'm not quite sure what you're saying, but if so, you've got two particles in an entangled state, and they're now a long way apart, and then you measure something here, then you know that when the person measures it over there, they're going to measure, the correlated spin. But that doesn't enable you to transmit information, because you don't know what you're going to measure until you measure it. If you could make yourself measure something, then you'd know what they measure over there. But that's not what quantum mechanics tells you. So it doesn't provide any way of transmitting information. So it doesn't violate relativity.
So the Copenhagen interpretation has traditionally been the most popular amongst physicists. However, recent polls amongst the physics community show growing support for other interpretations, such as many worlds and Bohm's interpretation. Do you think there'll be a shift away from the orthodox Copenhagen interpretation in the future?
Yeah, I don't think the many worlds will take off. It just seems so extravagant, and it doesn't give you anything. It doesn't give you anything more useful than the Copenhagen interpretation, in that you can't go from one of these universes to another. We're stuck in a particular track in that model, and so you're creating all these other universes in your theory for no gain. But I think I would hope that decoherence would become more solid. Certainly there's a lot more research done into it, and it really was only in the 1980s that it started, and you can find lots of papers discussing the behavior of systems as they decohere now.
So during an observation, a quantum system interacts with a laboratory device, which is often treated in a classical manner. Must the apparatus making the measurement also be treated in a quantum way? Could this be a possibility?
I mean, this is Schrodinger's cat again. You know, what is a measurement, and where do we go from? So if you say a measurement is with a macroscopic device, you know, instead of consciousness, you say the measurement is a macroscopic device. Well, why can't you describe that macroscopic device by quantum mechanics? Surely you can, and it's just a more complicated system. So it doesn't solve any problems. It just illustrates that there is a problem with the Copenhagen interpretation. In decoherence, which I say is not a full model, then it would tell you that because you're interacting with so many particles in the measurement apparatus, that the initial states decohere and become much more like the classical states. But it still doesn't really solve how you go from an entangled system to an actual measurement.
So does this put a sort of limit on our ability to come up with let's say, a complete theory of the universe, which describes the universe through a quantum model?
I don't think so, because as I say, even the Copenhagen interpretation, that to me doesn't seem like the full picture. Still, all observations you can possibly make will be consistent with it. So, you know, it doesn't actually alter the predictive properties of the model. And yet it's a very successful model, so I don't see any reason why we can't. I mean, we don't have a quantum model for gravity at the moment, but I don't think it's a fault with the interpretation of quantum mechanics. We just need the right physics for the model of gravity.
So how do we know that particles exist in a superposition if a measurement causes the superposition to collapse?
So there are experiments you can do where, okay, in any particular state, you don't know what the measurement's going to be, and you're going to make one measurement. But if you set up systems in the same state and you make measurements, repeated measurements, then the statistics are different. And this is like Bell's inequality. You can actually do an experiment where if they weren't in a superposition, you would get a different result. And this is what kills the hidden variable theories. So you in your previous question, you might be saying, all right, because we're taking quantum mechanics, we're not allowing a hidden variable that if we knew about it would give us a more complete model. But you know, these experiments that have made Bell's inequality a real measurable experiment show that hidden value theories are just wrong.
Do you have any questions?
I think that's pretty good, yeah.
That's great. Yeah, that's great.
Yeah, thanks very much.
Thank you.
Thank you.